So in today's tutorial, we are going to be covering this effect, fireworks for days. So how do we get this effect? What is the main thing that we're trying to do here? Well, we need to create a bunch of particles on the screen and then have them expand outwards in a circular motion, similar to like what we did for the particle tunnel tutorial, but this time we need to randomize that outward expansion to get what we're seeing right here. We're also going to add in some deceleration for these particles. You see they get a little slower as they go out, and we're also going to make sure that they start traveling downwards with a little bit of gravity. So we're kind of combining a bunch of tutorials together right here. So to get started, we're going to be here with a blank canvas boilerplate. Simple enough. Very first thing we're going to do is always get rid of the code we do and don't need. So we're just going to go top to bottom here. Well, we need to track our mouse because we're going to be basically going back and forth to click where we want the explosions to be created at. We don't need anything related to colors because we're going to generate that automatically. Our event listeners, we don't need anything related to mouse move. We're going to use a click event listener. And for resize, we should pretty much always keep this, so we're going to leave that as is. And it looks like the rest of this is good to go, but we can go ahead and get rid of this text HTML canvas boilerplate at the very bottom. So first thing we need to do is actually create the individual object that we're going to be using to create this explosion. And to create an individual object, well, we don't want a generic object class. What we want is a particle class, because these particles are basically what an explosion actually consists of. So default stuff here, pretty basic. We've gone over this in a lot of other tutorials, but to refresh your memory, constructor is created every time we instantiate a new object from this particle class, and this particle has different properties inside of it, such as x, y, radius, and color. But to get this effect, we're going to need to add a few more properties, and we'll do this as we go so you understand when we need to implement them within this piece. But for now, let's go ahead and keep this particle class as is and get right onto the implementation. So actually getting some particles spawning on the screen, doesn't really matter where, but let's go ahead and spawn them on the screen whenever we click at a specific location. So in order to render out our particles, we need some sort of container for these particles, and a great container for objects or particles, for instance, is always going to be some sort of array. But right now we are storing just a default objects let as this array. And this is just too generic for what we want to do here. We want to make sure that we're changing objects to particles so we know exactly what is inside this array, because this is where we're going to be spawning the particle objects. And inside of this for loop is basically how we're going to spawn these particles. So basically what this is saying on init, whenever our canvas is loaded, we want to run through this for loop 400 times and do whatever we say inside of this code. But we don't want to spawn anything. You'll see when I refresh the page, we don't want to spawn anything on init. We actually want to spawn things whenever we click on the canvas. So we don't actually need to spawn anything within this init function. We're going to go ahead and cut out this for loop, and at the very bottom beneath animate, we're going to go ahead and add in an event listener for clicking. So to add in an event listener, typically you would do window.add event listener, then you would specify your event and what happens as this event occurs. Now if you want to know a little trick, since we are using a property on this window object, well, we don't actually need to put this window object in there. You'll see our resize event listener doesn't have window prepended to it. So a quick little trick to make your code just a little cleaner is you can go ahead and get rid of that window object altogether, and this is still going to work. So let's go ahead and get rid of that window object. We want to specify we're going to spawn particles on click. But just to test that this works, it's always safe to go ahead and add in a console log statement. So we'll just say go. Check our console, and now when we click our blank canvas, we're going to see go being created over and over again. So we're going to go ahead and get rid of go, paste in our for loop, and we're saying whenever we click on the canvas, we want to run through this for loop 400 times and create a new particle for each iteration of this for loop. So we're going to be creating 400 particles each time we click on the canvas and storing them within this particles array, which we will soon render. But first thing first, we need to push these particles inside of the array. And we look at the results in the browser, open up our object, you'll see we have two properties in here, client X and client Y. Well, when I clicked, these are the locations of my mouse, exactly where I clicked on the canvas relative to the very top left-hand corner of the screen. So when I clicked on screen, my x coordinate was 280 and my y coordinate was 127. So we need to make sure we're referencing our event objects, client x and client y properties, in order to spawn our particles in that exact location. So if we scroll up to the very top, you'll see within the canvas boilerplate we already have a mouse object, and this is just assigning x and y coordinates to the very middle of the canvas. Well, we want this mouse object, so our mouse x, to be equal to our event objects, client x, because that is where we clicked on the screen. Basically, we're just storing this inside of an object property that is a little more descriptive than just event.clientx. So we're going to do the same thing for our y coordinate and store client y inside of mouse.y. And now when we console log out our mouse object, whenever we click on the screen, you'll see that it goes ahead and logs out location of our mouse exactly where we click. If I get really close to the top left hand corner, well, we're almost near 0, 0. So this is working perfectly. Now we actually want to spawn our particles at these locations. So our particles x coordinate is going to be mouse.x, while our particles y coordinate is going to be mouse.y. What is the radius for these particles in which we want to spawn? It can be anything you want. I'm just going to go ahead and start with 5, and I'm pretty sure I'm going to use blue for my default color. It seems to be the thing I go to by default. So now, when I click the screen, nothing's happening because we aren't actually rendering these particles. But if I go ahead and console log out particles on each click, you'll see that we are continuously populating particles into it. So perfect. Now we just need to actually render these out on the screen. So what we can do is uncomment out, and we know we're not referencing any default objects array. So instead of objects, we are using particles, and we want to say for each particle within this array, call the particles update function, which is this guy right here, which in return calls draw, and this is all the code that renders out each individual particle. So if I save this, refresh the page over here, and then click, you'll see we are spawning 400 particles wherever we click at the mouse's x and y coordinate. So this is looking pretty good so far, but now we need to create that effect of these expanding outwards. So whenever you need some sort of particle to start moving across the screen, you need some sort of velocity involved within your object. So what we're going to do is add on another property, and this is going to be called velocity, and it's going to be equal to a velocity argument, which we're going to pass through our constructor function. So now that we added a new argument, whenever we create our particles, we also need to pass through a velocity. And this velocity is going to be an object with an x and y value inside of it, because we want a separate x and y velocity to make sure that we can move these in different directions. So our x velocity, let's just go ahead and start with 0, and then add on a y velocity for 0 as well. And just to test that these are actually moving, I'm actually going to change both of these to 1, because we can't actually move anything with a velocity of 0, unfortunately. So now that this velocity is being passed through each individual particle's constructor and being assigned to this individual particle's velocity property, we can now make use of it within our update function. And this is basically an arbitrarily named function in which we want to move or manipulate our particles' properties. So the property we want to manipulate is going to be our particles x and y coordinates. And whenever you are adding speed or some kind of movement to a particle, you want to take the current x coordinate and add on the velocity. So we're adding on this dot x plus this dot velocity x, because we are passing through velocity as an object down here, so we reference the x value. And when we do that and click on the screen, you'll see that our particle begins moving right because it has an x velocity of 1 being added for each iteration of the particle in this animate loop. So we want to do the exact same thing for our particle's y coordinate. And when we do that, now things are moving downwards because we're adding 1 onto each individual particle's y coordinate as well. But we want to create that loop expansion effect. And to do that, we need to know a little bit of trigonometry, which we just covered in the particle tunnel tutorial. You can also learn more about this in the circular motion tutorial if you really want to get an in-depth understanding. But for brevity, we'll go ahead and do this pretty quickly, and I'll try to explain it the best I can. So whenever we click, we need to get some point along a circle's edge. And to get that point, we use sine and cosine functions. And those are just two functions that return any value from -1 to 1. And they are always going to be related to each other in some way. And we can use these values to assign a x velocity and y velocity to each individual particle to move them in different directions along a circle. And this is going to create a ring effect. So the very first thing we need to do is get the radians at which we're going to shoot each individual particle from the center. And radians is just a fancy word for angles. So a full circle is composed of 360 degrees basically. That is equal to 2 pi radians, about 6.28 radians. What we need to do is get the angle for as many particles as we'd like to have along the circle's edge. So hypothetically, let's say since our circle is 360 degrees, we have 10 particles and we want to place them evenly along a circle's edge. Well, we would divide 360 by 10 and that would give us about 36 degrees for each angle as we begin going along the unit circle. Hopefully that makes a little sense. Maybe it'll make more sense as I begin coding this. We'll find out. So what we want to say is our angle increment. This is what we're going to be incrementing our angle by as we run through this for loop to make sure our particles are all placed evenly. It's going to be equal to math pi times 2, which is 6.28. That is the full length of a circle. And then we want to divide by 400 because that is our particle count. Now, since we are using 402 places, and this references how many times we are spawning a particle, it's good to create a variable for this so we don't have to change it in 2 places. So our variable, or constant, is going to be particle count, and it's going to be equal to 400. And now that we have this constant, we can go ahead and replace the other 400s within our code. And this should still function exactly the same, which it does. We haven't actually implemented this angle increment just yet, but now we're going to do just that. So if we want to give our particle an x velocity that is basically going to send it at some different point along the unit circle, we can use math.cosine, because cosine is basically always for the x value, and then input angle increment right here. And if we console log this out to see exactly what it does, and not ath but math, and click, you'll see we're always getting a value of 0.9998. So if we are using the same value for every 400 particles, well, we need to make sure this value is different basically in order to get that loop effect. And to make sure that this value is different, well, if we look at the contents of our angle increment and refresh the page, click, you'll see it's equal to 0.0157. Now, what happens when I take 0.0157 and multiply it by 400? Well, we get 6.28, and that is equal to the full unit circle. Perfect. So what we want to do is, for each iteration of this loop, we want to multiply angle increment by whatever iteration we're going through. So that's going to be equal to I. And when we save this, this is going to force math cosine to pulse between values anywhere from -1 to 1. And we add that on to our x velocity, while we're going to get all these going in a different direction. So you'll see if I click, well, now everything is going in a different x direction. We want to do the same thing for y. And whenever we use some sort of sine cosine value for y, we always want to make sure that it is sine. So we'll set angle increment to be multiplied by I, and now when we click, we get that ring effect that we're looking for, very similar to what we did in the particle tunnel video. But now we want to add some sort of randomness onto this. You'll see in the actual simulation that we don't have just a perfect circle. Everything is randomized to some degree, and this is definitely what we want to go for. So this is actually an easy implementation. To add some randomness to this, all we have to do is multiply our x and our y values right here by math.random, which is always going to return a result anywhere from 0 to 1. So we multiply both our x and y by math.random. Instead of getting that mad pulse effect, we're going to get more of a random pulse effect from the middle. We're affecting the x and y velocities of each individual particle, and since those are different, they're going to go at different speeds from the center, but they're still going to go outwards in some sort of motion that resembles a ring. So we get that randomness effect that we're looking at right now. So we're going to go ahead and keep this, but let's go ahead and start making this look more like fireworks. We all know fireworks happen in the night sky, not a bright white sky. At least they're not supposed to happen in the white sky. So what we're going to do is, instead of using clear rect, which basically just clears the canvas, adds in that white background over and over again, we're going to replace this with fill rect and make sure that our fill style is equal to an RGBA value. And this takes red, green, blue alpha values, and red RGB values are always anything from 0 to 255. And if we want a dark value, we're going to go with 0 and set our alpha to 1. And this should give us a black background, which it does, but we don't really have any fade like we did in the simulation. If we look closely over here, you'll see when I click that there are light trails following each individual particle, and that looks really cool. That's something we want here, but we don't really have it just yet. So in order to get this effect, we can go ahead and affect our alpha value when we are filling in the background of the canvas. And what this is going to do is basically draw over each individual particle's past rendering. And as we do that over time, we create a light effect for each particle no matter where it goes. It just makes creating this effect so easy. So we're going to go ahead and put in an alpha value of 0.05. And now when we spawn our particles, you'll see we get that nice fading trail effect, which is absolutely perfect for what we're trying to do here. So we're looking pretty good, but one thing we want to do is start making these particles fall towards the ground, and we want to make sure that they are slowing down over time. Right now, their velocities just remain the same, which means that they're going to be traveling at the same rate. But eventually, particles slow down in real life, so we want to make sure we're adding some sort of friction onto them. And we're going to do that through our update function. So the very first thing I'm going to do is create a constant called gravity, and set this equal to 0.01. And then our friction is going to be equal to 0.99. You'll see how we use these in just a second. So if I go ahead and scroll down right here, gravity is a constant downward motion added onto our y velocity. So in order to get an effect of gravity, we need to make sure that we're affecting our y velocity over time. So what we'll say is this dot velocity y is going to be equal to itself plus our gravity value right here. Oops, gravity. So when we add this on there, and we go ahead and start creating particles, you see that they automatically start falling downwards, and this is all dependent on the strength of our gravity. If I go ahead and make our gravity 1, well, our velocity is just going to keep adding 1 onto it, which is going to make it fall really, really quickly. It makes a cool kind of like waterfall teardrop effect. But if we want to create something that's similar to fireworks per se, we would want to keep this around 0.05, 0.01, something that allows them to float a little bit before going back towards the earth. So I'm actually going to set this at 0.5, not too much gravity, but enough to get them to start falling down over time. You'll see it starts falling, and that looks pretty good to me. But they're not really slowing down. Even if they might look like they're slowing down, they're not. The velocities remain the same, except for y, because we're adding gravity onto it. We need to make sure that we are slowing these velocities down using some sort of friction. So it's going to be the same sort of deal. To create some sort of deceleration, we need to make sure we are altering our velocity for each iteration of our update function. So what we'll say is this dot velocity dot x is going to be equal to itself times friction. So if we make it equal to itself times friction, which is going to be 0.99, it's just going to slow down over time, because let's say our velocity is 10, and we multiply that by 0.99, we're going to get 9.99. And when we multiply 9.99 by 0.99, we're going to get an even smaller number. So for each iteration, we're just going to get smaller and smaller, which means our velocity is going to get slower and slower. So we do this for both our x and our y. Save this, and then click. You're going to see that these slow down over time. And this is actually more apparent than I thought it would be compared to what we had previously. Now, the x velocities definitely slow down over time. You'll see that they eventually stop, but our y velocity never stops because we are constantly adding on gravity to this. So to get a true effect of fireworks in the sky, what we want to do here, instead of these going directly to the bottom and off the screen, we want to make sure that these fade out over time. And the cool thing is once we make these fade out over time, we can do garbage collection and remove these from our particles array altogether, which is just going to make sure that our canvas piece is 100% performant as can be. So what we're going to do here is add on another property for each individual particle, and this is going to be an opacity property. And you can also call it alpha if you like. probably stay with alpha because I know Canvas uses alpha as well. So our alpha property is going to be equal to 1. Alpha ranges from 0 to 1, and that just determines how transparent each particle is. Is it semi-transparent, fully transparent, or not there at all? So in order to use this property for each individual particle, we need to go inside of our draw function, use csave. At the very end, we're going to use crestore. And then right before our begin path, we're going to set our canvas alpha value, which is going to be c global alpha equal to this alpha, this particle's individual alpha. So what we're doing here is we are saving, whenever we draw this one particle, we are saving that location in the canvas so we can make use of canvas's global alpha property. If we weren't using save here, well, we'd be affecting the alpha of the whole canvas together, but we really just want to affect the alpha of each individual particle. There's no real alpha function with canvas for drawing particles that I'm aware of, so we kind of have to do it this way with save and global alpha instead. But if we do this, you'll see clicking, everything remains the same, but over time we select our alpha value and start subtracting some sort of number from this. You'll see eventually that they fade out, and that might have been a little hard to see. I'm actually going to change this to 0.005 to make this a little slower. But if you look very closely, they start to fade out, they're gone, and then they reappear. Now the reappearance here is happening because eventually, as time goes on, alpha is going to be a number less than 0, and if you use a number less than 0 for global alpha, well, things just reappear, it bugs out, and it's not good. So what we're going to do is, if our alpha value for any particle hits 0, well, we're going to remove it from our particles array altogether, and it's just not going to exist, so we can't even assign an alpha to global alpha in the first place. So in order to remove a particle, whenever its alpha value reaches 0, we can head down into our animate loop. We're actually rendering each individual particle, and we're going to basically say if particle, this one individual particle, has an alpha value less than 0, then we're going to splice it out. But you know, now that I look at this, it's probably easier if we write it this way. If our particle's alpha value is greater than 0, then we're going to update it. It's okay to update. But if it is not, if we start subtracting from this value and it's something less, then we're going to remove it from the particles array. So to remove anything from an array, the first thing we need to do is select that array and then use that array's splice function, which just removes it all from the array altogether. And in order to use the splice function, we need to specify what index should we actually remove an item at. So our index we can get using our for each's second argument, which is always going to be the index of the particle that we're looping through. So if we say, I want to remove this one index from our particles array, just one particle from this index, I can delete that old if statement. And then I go ahead and run the piece and start clicking around. Well, eventually these just fade out completely because we are removing them from our particles array altogether. And if you really want to see how this works behind the scenes, what we can do is console log out particles. View our canvas, click around, you'll see we have 400 right now, have 800 because they were still on the screen, and if I click again when everything fades out, we're back to 400 because those old ones were removed. It makes it as performant as possible while still allowing us to use that opacity effect. So next step would be to actually color up these particles to make sure that we're getting something that looks cool, like a firework. So to color these, we want to head to wherever we're instantiating our particles, which is right here. And instead of just instantiating each one with a blue color, we're going to use hue, saturation, lightness, which takes 3 values. A hue, which ranges anywhere from 0 to 360. A saturation, which is going to be 50%. That just determines how deep the color is. And then we have lightness, which determines how bright or dull the color is. So if we save this as is and click, well, we now have one reddish color. But in order to get an assortment of colors anywhere from 0 to 360, we have to edit this hue value right here. So instead of getting 0 for each iteration of our loop, we can get any value from 0 to 360 by saying math.random and then multiplying this by 360. So since math.random returns any value 0 through 1, if we multiply that by 360, now we're getting any value 0 through 360. Save this, refresh the page, click, you're going to notice that they're all black and they fade out really quickly. Bad, bad, bad. So to fix this, right now we're trying to call this code math.random times 360. within a string. If we're calling some sort of calculation like this, we need to make sure that we change this string to a template literal by changing our quotations to backticks. And whenever we do this, we can start doing computations in here by using a $, opening curly bracket, and then wrapping our computation with a closing curly bracket. So our computation is math.random times 360. We go ahead and do this now. Now we get all those cool looking colors that we had prior, and this looks more like confetti or like a Mac rainbow ball, but you know, we're getting there. It's cool. Now, I'm not really a fan of how big these fireworks are. I'm going to go ahead and decrease the radius to 3. Let's see if I can get that looking a little better. I am a little happier with that. That looks more like a firework to me. So we could honestly like end it at this, but I want to show you how to start affecting the properties of our animation right here to really make this look like a expanding, powerful firework. Because I don't want no weak shit. I want some of that powerful shit. So if we're looking to make this more powerful, have these expand outwards at a quicker rate, we want to focus on our spawning of our X and Y velocities, which are these two guys right here. So right now, if we go ahead and go through each iteration of our for loop 400 times, well, the result produced from math cosine and math random here is only going to be something that's like -222, which is pretty slow. So what we can do to start adding on speed to this is multiplying this by a factor of whatever number we would like. And this is basically the power. This number right here represents how quickly we actually want these to shoot at. So if we go ahead and specify we want these to shoot at a power of like 8, well, we're already going to get a result that's pretty much identical to what we have over here. Well, pretty close to it at least. It might be a little quicker on that one. But that's all we have to do is just edit this one power property. And since this is being used in 2 places, we can go ahead and create a new constant called power. Set this equal to 8. Replace 8 right here. And now we only have to edit power in 1 place. So we can start experimenting with all these guys right here to really see how it affects our fireworks. So if we change power to something like 15, they're going to go even faster. You'll see fast, fast, fast. Let's go ahead and push this to the limit. So let's go ahead and make power 40. Oh my god, it's freaking crazy. If we really, really want to push this to the limits, we can go ahead and up the particle count. Something like 2,000. Gonna be crazy. Oh my god. Like, I'm like in awe right now just playing with this because I didn't even try this before this tutorial, but I really like it. It's so cool. Let's push to the limits, boys. 5,000 particles. How many particles does it take to lag up my entire computer? We're going to find out. So, oh boy, that might be enough. But that was like multiple clicks. I want to make 14,000 particles. Go ahead and click now. This is this is ridiculous at this point. So you can really play around with this a lot just by editing the particle count, the power, and just having fun with it. Yeah, like it's pretty much all you need to do. Start creating particles and fireworks in different locations. So I hope you enjoyed this tutorial. I hope you learned a little bit about creating particles with velocities that expand in a ring, and then using friction, gravity, and more to create an actual effect that looks good and that emulates a firework in the night sky. So as always, cheap plug incoming. If you would like to learn more about Canvas, web app development in general, then go ahead and be sure to check out chriscourses.com. This is a web development education platform I developed a while back and have been adding content to ever since. Basically, I have a couple free and premium courses on here that you can subscribe to really take your web app development, your Canvas development to the next level. Basically, all the tutorials on the site will teach you how to develop things such as user authentication, logging in, logging out, everything you need to build your own app, something like Facebook, Gmail, etc. I pretty much teach you how to do exactly that. So be sure to check it out. Be sure to ask me if you have any questions. I have a forum right here in which you can post all your Canvas, Node, Vue questions to, and I will be sure to answer. Otherwise, hope you enjoyed, and I'll see you in the next video. Peace.